prepared three topics, right? So this topic was supposed to be in the first talk, right? So this topic is about linearly. It's a two-stage stochastic program, but then has to do with linear biparametrized quadratic recourse. Okay, so this is the problem, right? So you have the now. Okay. So this is a deterministic function, and you have a recourse function here. Okay, but this recourse function is in this paper. The recourse function is linearly, meaning that you have x here appears linearly. Biparametrized, meaning that x occurs in both the objective and constraints, and the objective here, this function here, is quadratic. Okay. So that's the first topic I prepared. It's a two-stage, because there's a recourse function, and stochastic program, right? So the traditional stochastic program is that you don't have x here. You don't have x in objective. So that's the first topic. You guys can decide, okay? Later on, so I also prepare a second. So this paper is kind of old. Well, I say it's old because it was 2020, okay? 2020. Published in 2020, we work on this. And it involves additional Professor Sen, who's an expert in stochastic programming. And then you can see that Junyi and Ying, they both are part of the authors. So that's the first topic. The second topic is about risk. Okay, so we talk about interval CVAR. Now remember interval CVAR involves the difference of two CVARs. So Professor Wright just informed me that CVAR is no longer in vogue, right? So, but I continue to use CVAR. Anyway, so the interval CVAR involves the difference of two CVARs, so, and they are stochastic value functions. And we talk about this too. So they give you the example. So this is the problem that we deal with, right? So you can have this is regression. So you have a one-sided regression. This is like underestimation, and the other is overestimation. And you can have different weights associated with underestimation and overestimation. Okay, so they can have asymmetric weights. So this is the second paper. Okay, that we talk about this optimizing this interval CVAR. We need to determine theta. Okay? Yeah. Okay, so that's the second topic. And that was, oh, no. This was published recently, okay, 2022. And it was done maybe when Junyi was still at USC. Okay? So the third topic was supposed to be chance constraint, right? So this was supposed to be the topic for the second lecture. And you can see that it's published it was recently published, okay? And it was published in the set values, not, the paper is quite long. You can see this is about 60-some pages. And for a paper of 60-some pages, we find no outlets. We cannot publish in math programming. We cannot publish in Sci-Op. And so we chose a friendly journal, which allows long papers. And that's why the paper was published in Journal of Convex Analysis. Okay? So math programming does not allow, Sci-Op does not allow those long papers. So, what? I don't know. I'll let you handle it, maybe. I should have. Too late. Next time, Steve. Okay? You guys are witnesses. Okay? So next time, if I write a 70-page paper, I will send it to Steve. How about that? Okay. Anyway. Okay. So anyway, these are the three topics, and I probably should just talk about one. Okay? But here's the interesting part. I always like to make the talks a little bit light, right? So I'm claiming that for the Chinese audience, okay, you may prefer or you may not prefer chance constraint problems. Why? This is a little bit of riddle. So the non-Chinese, they may not know, but maybe they will know at the end. So does anyone figure out why you may or may not be interested in chance constraint problems? No? What's the abbreviation of chance constraint problems? Oh! Okay, so now should I talk or should I not talk about that? All right, so should I or should I not talk about that? Huh? Yes? Okay, so. Huh?
Singapore it's okay, not Hong Kong.
Okay, but still, I want to make sure there are no microphones, hidden microphones. Anyway, so this is academic. So actually, seriously, so this is a long paper. I mean, you can see 60. Maybe I should go back and just talk about an old paper. Now, the thing is that some of you may have, this paper is friendly in the sense that the mathematics is much simpler. Okay, the CCP paper, the mathematics is deep, it's hard. Okay, it's very complicated. Okay, so at the end, if you want to find out what CCP is, ask some of the people who know. Okay, so yeah, so I it's up to you, right? But anyway, there's a little danger. Okay, anyway, so let me talk about this probably, right? So just a little sort of a light discussion or light sidetrack, right? Okay. Okay, so let me talk about this. The paper was maybe a few years old now. The mathematics is a little lighter, little easier. And so this is a problem I've shown you, right? So you have this, and you can make this, I just want to make this simple, right? So you can make this, so this is deterministic, and then you have the challenge is how to handle this. Okay. Now, what you see here is that this here, I assume that it is convex, and not strictly convex, not strongly convex. Okay, and so the idea here, so when we did the paper, we make a simplifying assumption that this is assumed to be finite basically everywhere on a set that contains X. So we don't need to find the recourse function is finite, but it may not be differentiable. Okay, and also the optimal solution may not be unique, because this is only a convex function, okay? But we assume that this is a finite, the recourse function is finite, okay? So that's the setting. Now, this function, as a function in X, the recourse function as a function in X, because you have X here, is not going to be convex, okay? And some of you actually probably have figured out, given my interest in this area, that when I look at this recourse function with X in both objective and constraints, well, I cannot do it here, right? If I do it here, you cannot see it. See, I'm too clever. I need to do it over here. Then you can see it. I cannot, this thing is not clever enough. If I point it on the screen, you don't see the green light, right? You see the green light? No. Oh, you see the green light? Oh, wonderful. Gee, then I thought you could not see the green light. Okay, so then I don't need to turn around. Okay, so I can just do it like this. Okay, so this function as a function in X is not going to be convex because you have X here and X there. Okay, but what it is, okay, and I'm sure that many of you will know that this function is piecewise linear quadratic. Okay, that you can given C, given the random, given this vector here, then this value function is going to be a piecewise linear quadratic function on the domain where this value function is finite. Okay, that many of you will know, but it's piecewise linear quadratic. But how is that related to convexity, right? Convexity or concavity. Turns out that every piecewise linear quadratic function is difference of convex. Okay, it's a difference of two convex functions. So you can, in principle, this value function, okay, this function is the difference of two convex functions in X. Okay? But the trouble is that if I ask you to write down those two convex functions, it's not going to be very useful. At least at this point, we don't know how to take advantage of those two convex functions and design computable or implementable algorithms. So conceptually, you know that this is going to be a difference of convex functions in X, but so far you cannot use it profitably in the design of computation algorithms. So what can we do? Well, but there is an easy case where you can write down the DC decomposition easily. And that's the case when you have the matrix Q is PD, positive definite. When the matrix Q is PD, that's a recourse function. When that's PD, then you actually have this DC decomposition, psi 1 minus psi 2. And psi 1 is the maximum of a concave function, but parameterized by X over here, linearly parameterized by X. Right? So there's an X here, there's an X here, and it's the maximum objective value of this. Basically, this is just a dual. Okay? And so this is going to be a convex function in X. And then this part is actually a quadratic function in X. So this is actually this minus this is a difference of two convex functions. But the concave part, the second part, is actually a nicely differentiable function. And we call this class of functions favorable DC functions. This is a class of DC functions, different convex functions, that is much easier to handle than a general DC function. Because a general DC function, the concave part may not be differentiable. This case, it is. Okay, so we in the book, we call this a favorable DC function. So in this case, you have this decomposition, and now it's easy to, not easy, but you can now design algorithms for it. Okay, so let's go on. Okay, so in this case, the two-stage SPE is really equal to a stochastic DC program. And you know the DC decomposition. This is a non-differentiable value function, but it's convex. And then this is nicely quadratic. Okay? And so now you have a DC function here, right? A DC function. Considering this as a deterministic function, okay? Considering it's a deterministic function, this is a DC function. And so now you can talk about stationarity concepts, okay? And there are two kinds, okay? There are two kinds of stationary concepts. There's the kind that is based on the directional derivative, okay? Because it's directionally differentiable. So we can talk about the so-called directional stationary point based on the one-sided directional derivative. That kind of directional derivative is very nice. It's very sharp. Okay. However, the drawback is that it's not easy to compute. Okay. It's not easy to compute. And in the DC literature in the 80s, okay, maybe the concept of critical point was introduced. Okay. Critical points are broadening. So you have directional stationary points here. You have the clock stationary points bigger, and then the critical points even bigger. Okay, even bigger. Okay, so what I suggest to Anthony yesterday was that a lot of the results are based on that he had difficulty really dealing with the full set of results he wants with the clock stationary solutions. But at least for DC problems, the possibility of dealing with this kind of complexity analysis with critical points, I think is within reach. In fact, it probably would not surprise me that already has been done, okay, by the original French, the Vietnamese group in France. Okay, I don't know, but the critical points, the set of critical points is much bigger. Okay, and it has all kinds of convexity properties that one can exploit. So for complexity analysis, dealing with critical points is much more promising, I think. Okay, I don't know, okay? I don't know. But anyway, so in this context, we have these two kind of stationary concepts, and which one do we want to compute, right? Now, in this case, we're lucky because the concave part is differentiable. Turns out that there's no distinction. The two concepts are the same because the concave part is differentiable. Okay? So now this is the method that I sort of gave this different methods to deal with this. Notice I don't need to approximate here because the functions are all, there's no discontinuity, things like that. So I don't have that. And then because in this part, the set X is a constant set, right? So it's you can make it closed convex, you can make it polyhedron. So I don't need penalization, okay? And I'm not going to penalize X because X is taken to be a polyhedron, for example. So I basically just need the approximation of the expectation, which I'm doing with sampling, and then I use the surrogation to deal with the difference of convex. And for difference of convex functions, surrogation is easy, especially the concave part because the concave part is differentiable. Okay, surrogation is very easy. Okay, so this is a standard sort of surrogation for the concave part. Okay, so this is the first step is the sampling, right? So you replace it by the samples, and then you're going to linearize this part, okay? And that will give you a majorization. And so this would be your surrogation function. And so when you have a DC function with a concave part, then the surrogation by a convex function is easy. And you just need to linearize the concave part, okay? So now once you have that, then you have the combined SAA method with the standard DC algorithm. Okay, no big deal, right? So this is what you take a sequence of positive integers, okay, and then this would be the sample batches, the number of samples you take, and then at every iteration you generate in the ID samples and you solve a convex problem. So I still very much rely on convex programming methods. Okay, so any advances in convex programming I can borrow into the non-convex domain. Just one step. Just give you an example. You look at the CVX code, right? The Steve boy. Nowadays he can handle DC problems very easily. And the reason is exactly because this kind of linearization. You can create a sequence of convex problems very easily when you have DC structure. Okay? And this is that, but this here, the complication is because of the expectation thing, and which you can do by just this extra step of sampling. Now, I want to go back to this baby steps. Okay, so what we have done really very simplistic. Okay, I mean there are a lot of bright minds out there. I'm sure that you can do better than what we have done, but at least we have taken a first step to try to handle this. Right? Okay, so this is a very straightforward kind of sample average plus DCA. Okay, and then you can prove convergence. This is again subsequential convergence, and in the sequence of this, almost surely, okay, this is almost sure convergence, right? But this is almost sure subsequential convergence. Okay, again, that's the result we have. We don't have a complex analysis, nothing. Basically, this is the thing, because this is the easy case. Okay, and then there's some technical notes I can. This is the Polygon or directional differentiability is in terms of the directional in terms of this directional derivative. Okay, so I'm going to skip this. Okay, this is the challenging case. Okay, the PSD, because the PSD case is that I'm interested in the just focus on the domain of finiteness. Okay, so now this here is not, and so what we did is that we used this notion of separating out the variables. You have X in the objective, you have X in the constraint. And why don't we define two variables? You have z here, and then you have x here. So now this becomes a trivariate function. So this is a lifted recourse function. Okay? And the usefulness of this is that if I look at this, then when this two x is equal to z, you're going to recover the original objective. Okay? You're going to recover that when x is equal to z. The other thing is that when you fix z, then this is going to be convex in x. And when you fix x, this is going to be concave in, so think about DC, right? DC is convex minus convex. If I fix the second component, the concave part, it's convex. When I fix the first component, it's concave. This is a generalization. This kind of a function is that this function is, the original function is derived. It's derived from this lifted function. And the lifted function has this convexity concavity property, except that it is not explicit. In the DC case, the convexity concavity is explicit. This one is not. Okay? And so we call this the implicit. So here's a question for you, right? So my co-author says that this should be called implicitly convex concave. And I said that maybe we should just call it implicit convex concave. What do you prefer? Should it be implicitly convex concave? We asked the English speaker here.
Well, I think it's right there. Implicit is
Right, so this one is correct. This one is correct because I use now. Right? But when you say implicit convex concave function, or do you say implicitly convex? Okay, anyway, so this is just a side thing. I'm sorry, I try not to be too serious. So anyway, so okay, this is okay. So this function here, original recourse function, is implicitly convex concave. Generalization, a class of non-smooth functions, a non-convex function that generalize the DC functions. Okay. So now what we have is that we say that this is a generalized critical point. Why is it so? Critical point is that is actually the subdifferential of the first component minus the subdifferential of the second component in the DC case. Here, because this function is not, we don't know the representation, so this is how we define. So this is exactly like the generalized critical, exactly the critical point idea, except that we utilize this and because it's differentiable, it is concave in the z variable, right? So I can take the subdifferential in the convex analysis in the convex sense, and then make this negative. So this is a convex function in the second component. I fix the first component x bar and take the subdifferential, convex subdifferential with respect to the second component. And a vector is said to be a generalized critical point if this is the usual generalization is the generalization of a critical point when you have a DC function. But when you don't have the explicit DC structure, this is what we do. You take advantage of this, and then you look at this point. Now, when we know conditions under which a generalized critical becomes a directional, because if the second part basically, for example, when this subdifferential here is a singleton, okay, when this is a singleton, so we're going to recover the directional station point. So, and that means that you basically have to do with unique multipliers or something. Okay? So I forget which one. Okay, so equivalent, this is an equivalent function. Now, this is very important. Okay, this, although I write it in this way, you may not see the significance of this. So what you see here, so I want to give you the insights of this stationary condition. What this is saying, if I look at this, okay, if I look at arc mean of this, okay, you fix x bar, and this is a convex function in x. Okay, this is a convex function in x. Okay, and I'm defining a generalized critical point as a fixed point of a optimal solution mapping of a convex problem. Okay, this is a convex problem. Okay, and this convex problem is parameterized by x bar, by a given point. And what this says is that X bar is a fixed point, okay, of the admin set of that convex program. And so now I'm using this idea of surrogation. So this is in a way a surrogation. I'm using a surrogation function which gives me a convex program. This surrogation function is parameterized by a point. So now you have a mapping. Given X bar, I have this admin set. Okay, so this is and a fixed point of this admin mapping is defined to be a stationary point. So this, in a way, is the insight is because this thinking is very. If you think about, you know what you know. For example, in the differentiable case, okay, when you have differentiable functions, a stationary point is gradient equals 0. Gradient equals 0. But you can look at this. Okay, you look at the gradient equals 0 as a fixed point of an algorithmic map, where the algorithm, as a fixed point of a mapping, of an admin mapping, where that admin comes from a convex program. This is a very important, I think, the way how to deal with sort of non-convex functions. You have a surrogation function. The surrogation functions give you global mean that you can compute, okay? And then you define a stationary point of the original non-convex problem as a fixed point of that mapping. So when we did this at the time of the paper, we didn't realize this. But actually, I think that this is a very useful way to think about what is meant as a stationary, as a necessary condition of optimality for non-convex problem. You can say this a little bit cheating, but because I use convex thing, but you can compute this. Okay, so this is the algorithm. Okay, so now how do I accomplish this? So I need to define a regularize. Okay, so I regularize this objective. So now I make it positive definite, and then now I can get the DC decomposition of this regularized recourse function. Okay, regularized recourse function. So, and I can get this DC decomposition, and then now I do all these things together. Do sampling, okay, regularization, alpha, and then here you have linearization. That's a DC decomposition. And so now I end up with this subproblem. This subproblem here is a convex program. Okay, it's a convex program. Now, I'm not saying how to solve it. Okay, in the paper, we actually have done some numerical study of how to deal with this. But at this point, this is a conceptual. I know that I can do it, but then, of course, how well I can do it, I will depend on you guys. Okay, because I need to solve convex subproblems. Okay, and that part is that I hide it. So, and then you can. So you take this. You take a scalar, a sequence of positive scalars for the regularization, and then under a condition on this regularization alpha here on this regularization, this is proximal. This is different. Okay, this is a proximal step, but then this is a regularization step of making Q, turning Q into a positive definite matrix, and then you can prove almost sure convergence to a generalized critical point. If there's under this condition on the regularization step, has to grow at least the square root of the number, and then you have this condition on that connects the regularization parameter with the samples. Now, again, this is it's a very preliminary step to try to get some kind of convergence results. I'm sure that if you look at this, continue looking, doing more research of this, I'm sure you can do better. And maybe you can even derive some complexity results. We have not done that. Okay. So I have maybe 10 minutes. I want to finish talking about this interval CVAR. Okay? Because it's a little bit different. Okay, so this is you have the CVAR, or quantile. This is a super quantile, right? That's a CVAR super quantile. Okay. Okay, so I want to minimize this in CVAR, okay, interval CVAR. Of this, here you can think of this as, is it under or over? When this is positive, then you actually overestimation. Okay, when it's positive, then you have the output. So this is the overestimation error, and this part here is the underestimation error, and I'm separating the two. I'm assigning different weights to the underestimation and overestimation. Okay, so this is this is robust regression because using this interval CVAR, there's a chance of handling the over and underestimation errors as well as handling outliers in different ways. And in the paper, we actually take this. This is a statistical model, okay, underlying statistical model. We take this to be a difference of convex functions. So, for example, this underlying statistical model can be a piecewise affine function. Okay, so this is a problem that we address in that paper. It is an interval, and what this gives us is that now you substitute the formulas for the superquantile, the CVAR, and then you're going to end up with this optimization problem. Okay? You're minimizing this over the parameters, and then what you have here is that this function, you have expectation here, and then you have two parameters here, those because of the CVAR formula. Okay, the T1, T2, they come from the CVAR formulas. Okay, so you minimize this as a function, and this function, expectation of this are randomness, and then these are the dummy variables that come up in the CVAR formulas. Oh, okay, and this function will be jointly convex in this theta, which is the parameter of the problem, and also those dummy variables. And because of this joint convexity, the whole thing will be a convex function in theta. Similarly, the second part. And so what you have here is that you have a optimization problem which involves the difference of two stochastic value functions. Okay, so question is, how do we optimize this? Okay, so this part is easy because this is convex, so I can just do a sampling of this. Okay, so I don't need to do anything special with this because when you do sample, you still end up with a convex function. And so you can now understand why I say that. I mean, I hide a lot of the implementation details. I rely on convex programming methods to solve convex subproblems. Okay, so this part here, when you do the sampling, I just need to do sampling here. But this part you need to be careful because I have a minus sign here. Doing sampling here, you're going to get something which is not enough. And so what we did is that we need to do sampling-based linear approximation. So you take the samples, and then you linearize. Okay, so this is, and then you linearize it. And now you need to take subgradient. So what we did is that you're given theta k, you're given the samples, okay, and I'm going to optimize this to get over my dummy variables. Okay, so now this is the convex programming step. And then once I have this, then I'm going to take a subdifferential of this value function, and I'm going to linearize it using this function of the concave part. So this is very much similar to what we did in the DC case, where you linearize the concave part, but here you need to do a little bit more work because this is a value function. Okay, so I cannot directly sort of linearize this. So I need to do need to solve a convex function, take a subgradient of that, and then you linearize that with respect to that concave function. So this is what we get. So it's a sampling-based linear approximation. Okay, so here's a complete algorithm. You have samples, and then we actually here we do an incremental sampling. And then you solve this has to do with the concave part. You first do a minimization of that, take a subgradient at that minimizer, and then you look at this. This is now a convex problem. Okay, so this is the overall algorithm involves linearization, But then it's a little bit more complicated than just a DC because it is actually a stochastic value function. Okay, so sampling is involved, but then the linearization, we then need to resort to the usual DCA where you use the subgradients and not gradients. Okay, so what can you prove? Oh no, that's it. I did not talk. Okay, so I'm now 28, so I can either stop here. I can talk about a little bit about CCP. Okay, so maybe I'll talk a little bit about CCP. Okay. Okay, so here's CCP a little bit. Okay. Change constraint. Okay, so this is based on a very recent paper. So again, because you all remember what Steve said, right? So yeah. So anyway, so this is a long paper because the literature on change constraint is just huge. Okay, and so but what we hope is that we have done a comprehensive, a unified way of looking at this. So what we did. This is even a simpler model than what I showed you in the beginning. What I showed you in the beginning is what we are actually working right now. Okay, that instead of just probabilistic constraints, we have expectation constraints, and then expectation constraints inside can involve step functions. So this, in a way, this is like a standard change constraint program, but with a very important departure. It's a very significant departure from the vast literature on change constraints. So where is that departure? The departure here is that there are coefficients here, and these coefficients they can be plus or minus. Now, if you look at the literature on change constraint stochastic programs, the constraints the coefficients always one sign. Okay. So now you can ask, why just one sign? What happens when you have mixed signs here that combine these probability functions? Plus or minus, you can have plus or minus, no restriction on the signs. So this is a simple instance of a mixed sign that leads to this, where this coefficient actually has plus or minus, both in it. So this is a conditional probability constraint, right? This conditional probability has to be greater than or equal to B. Just pick something, right? So now if you want to clear this conditioning, then this is what you end up with. Okay? This constraint is equivalent to this constraint. So now what you see here is that in this constraint here, your B is positive, assuming B is positive. So you have positive coefficient, and then you have a negative coefficient. And so now you end up with a constraint that has the coefficients both positive and negative. In the literature, you don't see that. Okay? And another thing is that because of the conditioning, you actually end up with a non-differentiable operator that connects those functions. Okay? So you end up with this. Okay? So this gives you a little motivation of why we look at the case. There are others. For example, okay, I probably won't go into the details because I'll just give you a sort of a little insights. Okay, big picture, high level. All right, so if you look at another example, is that suppose I want to look at the probability where some events are excluded, exclusion of events. I'm interested in the probability of some events being excluded. So here, I'm interested in probability. So this will appear in the constraint, right? So this is less than or equal to something. Anyway, so I'm interested in this probability function, that this is greater than or equal to 0, but not this. Okay. So now when you write this, not this, then you end up with this, that this has been less than 0. Okay. So now I challenge you to try to write this in a nice way, without assuming 0 probability. I mean, you can assume that probably equal to 0 has equal to 0. The case where equal to 0 has 0 probability. If you do that, then you probably can add a horizontal line here. Okay, but I don't want to make assumption and try to see whether you can write this in terms of non-functions. This is strictly less than 0. Okay, it's not less than equal to. Now this is a formula, right? So this is a standard formula. Probability of A take out B, not B, is equal to this probability minus the intersection of that. There's a paper in the literature where they also analyze this kind of exclusion probability, but they simplify this. I forget which way. They drop one of those terms. They drop one of those terms. But this is exact. Okay? This formula is exact. And so now if I use this formula, then you end up with this. Okay? This is equal to this minus that. And now this, where the g function, because you need to combine f1 and f2, you end up with this g here being the mean of these two functions. Again, that's where you get the non-differentiable functions. Okay? So this is another example where you can use this kind of non-differentiable functions to model a lot of different things. You can model conjunctions, you can model disjunctions, you can model exclusions. Okay, so this is the summary here. You can have conjunctive, disjunctive combination of random inequalities. So this is conjunction, because I want this to be greater than equal to this and less than equal to that. That's conjunction. That's an N. But then this is or conjunction. So now this is combination of conjunctions and disjunctions. And you can also all model this using the max-min kind of thing. Okay? Non-differentiable. Okay, let me stop here. Okay, the rest is technical. Okay, how we actually deal with this. And it's 11:34. I have 11:30, right? So 4 minutes over time. I'm going to skip the rest. Those interested, I'm happy to. The paper is published. Okay. Thank you very much.